Hi, my name is Bianca Lopez Parnetti, and this is my presentation on Lab 4, bar magnets. The purpose of this experiment was to measure the distance dependence of the magnetic field due to a small bar magnet and compare it to the distance dependence predicted by the equations for the on and off-axis magnetic fields derived from the Biot-Savart law, and then to use a magnometer app to measure the magnetic field due to a permanent dipole moment. So, the fundamental physics principles used in this lab experiment were the Biot-Savart law, magnetic dipoles, and finally distance dependence. With all these meaning the magnetic field at a point for a small unit of charge, the magnetic dipoles being a closed circulation of electric current, then giving off a magnetic field, and then finally changes in the magnetic field due to differences in the distance. So this experiment was set up by orientating the phone and its magnetic sensor to the Earth's magnetic field, and then calculating changes in the measured magnetic field at different distances, both on-axis and off-axis, and to finally calculate the magnetic dipole moment of the bar magnet. And this was all done with the two equations at the bottom left, one of which was pulled out of a scatter plot graph, and then the bottom one being used in the computational model that I'll show shortly. For the on-axis results, I moved the magnometer to various distances which were just called R, and this data yielded a K value of 3.02 e to the negative 8, which is here at the bottom. This was used through the slope and the formula that I showed previously. And by plotting ln of b of x versus ln of r, I was able to solve for the slope, and which represented the distance dependence, and from there I calculated the magnetic moment mu to be 0.151 amps times meter square. So then that calculated value for the magnetic moment was the only initial condition for the glow script, but it was used to create a 3D visualization of the entire experiment online. And here with this little thing you can see that the orange arrows represent the on-axis field pointing away from the magnet, while the blue arrows represent the perpendicular field pointing in the opposite direction. I also modeled a 45-degree off-axis point, which was the little purple arrow here in the corner, to compare against the actual data, but everything's quite wonky because some of my data obviously came out to be a little bit incorrect. But for some common trends between the computational model and the actual experiment, some similarities were that both models showed a decrease in the magnetic field magnitude as the distance increased, which obviously makes sense. And then the on-axis arrows pointed in the same direction as the dipole moment, while the off-axis arrows pointed in the opposite direction. And one major difference or assumption is that the calculated model assumed a perfect system with only one magnetic influence from the bar magnet that we were measuring, which is not true in the real experiment since there were a lot of other different magnetic objects just in the room. So what I just mentioned is obviously a major source of error, but some other sources could be first, the errors with the magnetic sensor on the phone and how well it could pick up the changes in magnetic fields based on the distances. Secondly, obviously the influence of other magnetic objects in the lab room. Nothing was insanely strong, but just everything kind of has, well, not everything, but a bunch of objects have just random magnetic fields. And then third, the assumption that the bar magnet acted like a perfect dipole for the calculations later done in the glow script computational model. So going back to the original lab experiment instructions, here were the true observations for this experiment that we saw, and it was the first and last one, being when the magnometer is far away from the magnet, it measured a near zero magnetic field in the x direction. This was true, and as the magnometer moved closer to the magnet, the measured x component of the magnetic field increased. This was also true, and the other ones were that the moving closer to the magnet, the field decreased. That was false, and then the no effect was also false. It always has an effect. And then finally, for the additional questions on the lab report, first it asked what if you hadn't oriented the experiment to compensate for magnetic north and instead done whatever else. The results would have changed because they would have been influenced by the magnetic field of the Earth, so the data would have been completely skewed and would have been less accurate for measuring the magnetic moment of the bar magnet and specific. And then secondly, if we stuck just another magnet end on end to the one that we did and ran the experiment again, and how the measurements would differ, and the magnitude was just double in value, but the direction would be the same, so which is kind of expected. And that's it. Thank you so much for listening.